For the last chapter, we need to revise a few things about waves that you did in previous grades. Not so much, but I am going to focus on what you need to know. The two types of waves that you dealt with were longitudinal waves and transverse waves. Now, in this chapter, we're mainly going to focus on transverse waves, but just so that you remember the difference, you should remember from grade 10 that that looks quite funny. You should remember from grade 10 that a longitudinal wave was made, and you're welcome to do it on the slinky spring again today. Your teacher might pause and let you do it. The longitudinal wave, to make the wave, you need to push the slinky spring in this direction. So the disturbance was in this direction or this direction, but the wave then travels in this direction, and you can see that the direction of the wave is parallel to the disturbance causing the wave. For a transverse wave, if you want to create a wave like this, you need to pull it up or down, which means the disturbance forms a 90-degree angle with the direction of the wave. And that is how we distinguish between a longitudinal wave and a transverse wave. Longitudinal waves are basically sound waves, and we don't really deal with a lot of longitudinal waves. And you must please not confuse radio waves for sound waves, because radio waves is part of the electromagnetic spectrum that we're going to look at in a lot of detail, and it is a transverse wave, not a longitudinal wave. That's the difference again between those two. So the waves we're going to deal with are all electromagnetic waves, and they are all, like I said, seen as transverse waves. Not seen as transverse waves, they are transverse waves. And the terminology that you need to learn or remember for them is a wavelength. A wavelength is the distance, if you look back at the previous page, is the distance that it takes for one wave to pass a point. So that is the length of one wave, the wavelength. So the symbol for wavelength is lambda, and we measure wavelength in meters. Amplitude we're not really going to deal with. It's the maximum disturbance from the resting position. Not so important right now. Frequency, the symbol for frequency is F, and that tells us how many times per second something is happening. So for instance, if you are jumping up and down 10 times per second, by now you know that if we say per second, we can say that's 10, and we could use the unit seconds to the minus 1. This is not the common unit for frequency though. The unit that they use most commonly is the hertz, a capital H with a small z. So hertz is the same as per second, and it tells us how many times per second something has happened. Period here is very similar, but it tells us how long it takes for one of these things to happen. So you sitting in this class for one period, it's how long one lesson is. So yeah, it's going to, if you were jumping up and down 10 times per second and you want to know how long it takes for one jump, you should all figure out that would be, we're going to say that we take 1 second and we divide it by the 10 jumps. So that will tell us how long it took for one jump, and the unit for the period would just be seconds. So you should see now here that these are just inverses of each other. So if I have the period, I have the frequency, and vice versa. So period is 1 over frequency, and also frequency is equal to 1 over the period. Now the speed of a wave is super important. This is the one that you're going to deal with the most in this chapter. If you remember the equation for speed, speed is equal to distance over time, or displacement over time. Same old equation you've always used. If we look at one wave, we can say that the displacement is lambda because it's the wavelength, and we can say that the time that it takes for one wave is the period. So this gives us one equation, or a second equation already, to work out the speed of a wave. But now you can also see here that if I do this, 1 over t, we have just said, is equal to the frequency. So it gives us the wave equation that you did in grade 10 that says that the speed is equal to lambda times by the frequency. Now, because we are going to work with electromagnetic waves that are all similar to light waves, or they're all on the electromagnetic spectrum, we're going to assume that these light waves in a vacuum all travel at a constant speed, and therefore we can use the speed of light that's on your information sheet as c, and you'll see it's 3 times 10 to the 8 meters per second. C is then equal to the frequency times by the wavelength. And this is the equation that you are going to use mainly in this chapter. For the waves, there are other equations, but the one that you need to remember from grade 10. You also need to remember the electromagnetic spectrum, and that is why we are going to let you sing that song again that you all loved so much in grade 10. And your teacher is going to load the link to the YouTube song. And I'm hoping that you guys sing along better than you did in grade 10 when we did this the first time, because it's a karaoke song. And if you sang through it once, you should be able to tell me the use of every type of electromagnetic wave. And you should be able to tell me kind of which ones are dangerous, meaning high energy, and this is what you need to remember the most for the rest of the chapter, and which ones are not so dangerous, meaning low energy. And that is the main purpose of us doing it. So while you're listening to the song, take note of a use for at least one use for each of the electromagnetic waves, and take note of the ones that have high energy and the ones that have lower energy.